Hello, everyone, and welcome. Welcome, Leif, to today's webinar. Today's webinar, Freezing in Crystal16, Measuring Stochastic Ice Nucleation, is brought to you today by Leif Deck from ETH Zurich. Shortly, I will also introduce our speaker to you. But just before that, a bit of technical information related to this webinar that is being recorded. If you have any type of questions, please write us an email at info@crystallizationsystems.com, and we will do our best to answer all your questions or directly to our presenter. Just before we start, a little bit about Technobis Crystallization Systems for those of you that do not know our company. Technobis Crystallization Systems is a Dutch company located in the north of the Netherlands. It is a world-leading technology provider for solid-state research, process development, and formulation. In our portfolio, we have 3 products: the Crystal Breeder, Crystal16, and the Crystalline instrument. Some of you may already know the Crystal16 or the Crystalline, or both of them. If after this webinar you think that you would like to test one of these instruments, please contact us directly via the website or write an email at info@crystallizationsystems.com. Please remember the Crystal16, the one that you have here in the middle, multiple reactor system with 16 reactors working at 1 milliliter scale, is your instrument for solubility, metastable zone with induction time measurements, nucleation rate, phase diagram, screening, and the Crystalline, the one here on the right side, is your instrument with the camera technology that works exactly like a microscope. If you have a Raman spectrometer, you can easily connect it to this instrument, multiple reactor system, and you can follow chemical reactions or polymorphic transformation while you are actually performing your instruments. All our analytics are inline, nothing is in contact with you or with the sample. And the Crystal Breeder is the gadget type of instrument, how I like to call it, that comes with a lot of gadgets for vapor diffusion, evaporation, controlled evaporation, allowing you to actually perform most of the crystallization methods to grow single crystals, and not only that. And now I would like to introduce our speaker today, Leif Deck. He is pursuing his PhD at ETH Zurich in the group of Professor Marco Mazzotti in the field of crystallization applied to pharmaceutical manufacturing. Leif graduated from ETH Zurich in 2020 with a Master of Science in Chemical and Bioengineering. During his studies, he spent half a year at National University of Singapore and also another half year at MIT. I will not get more into details. You will hear more from Leif. And once again, thank you very much for bringing this topic and webinar today to our attendees. And I think now you should be able to share your slides.
Thanks a lot, Carmen, for the introduction and having me here today to share my work with you. Can you now see my slides?
Yes, perfect.
Yes. So then let me start. So as Carmen said, I would like to talk about freezing in the Crystal16. And if you remember the list of applications that Carmen showed before, freezing was actually not on the list of what this device is commonly used for. And as far as we know, we are actually the first group where we use the Crystal16 to do freezing measurements. So I think it's a very nice new application of this device that I would like to discuss a bit more specifically today. And I would like to focus on the measurement of stochastic ice nucleation. Let me start by giving a bit of background information. I'm a doctoral student in Professor Marco Mazzotti's lab at ETH Zurich, which is called the Separation Processes Laboratory. And the research group is on the one hand a very big group. So you see here 30 people or so. We typically have 15 to 20 doctoral students and then the same number of master students as well. And there are two main, let's say, topics of the research group. One is pharmaceutical crystallization, and the second one is carbon capture, utilization, and storage, which originally comes from adsorption research. Now, I'm part of the pharmaceutical crystallization group, where we have a couple of different topics. One of it is the work on pharmaceutical freezing and freeze drying, where I will talk about specifically today, where we use the Crystal16. We also have a couple of more classical crystallization topics, like crystal shape engineering, which is about understanding the effect that complex crystal shapes have on process performance, like needle-like crystals or platelet-like crystals. And we also work on more complex crystallization processes, like continuous crystallization and crystallization of chiral molecules, like the resolution of enantiomers. Now, what you will see also in my presentation today is that all these projects typically have multiple facets. So we have experimental work and modeling work. We have batch and continuous processes, although all the freezing work now is on batch. And we also have studies at multiple scales, from microscales to process scale. And this is something that will be highlighted very much for freezing. So let me give a one slide overview about why we actually care about freezing. And in the center of this slide, you see a vial containing the COVID-19 vaccine of Janssen. And what I should say is that our freezing research is actually in collaboration with the Janssen pharmaceutical companies of Johnson & Johnson. Because during the development of the COVID vaccines, they've actually realized that their freezing process design could not keep up with the demand for accelerated timelines. Now, if you have a biopharmaceutical like a COVID vaccine, but in practice it's for most biopharmaceuticals the case, you will run into issues with the shelf life of these products in a liquid state. So you commonly have to freeze them or freeze dry them. And the way this is done, because you have a large number of these small vials, is you may pack them into pallets where you have tens of thousands of vials and you put them then into a big cold storage room, or you put them into a freeze drying device where you will first have freezing and then drying at vacuum, whereby the drying at vacuum basically removes all the ice that you formed during freezing via sublimation. And both of these processes are commonly used. I will focus today on the pallet freezing process on the left, because this is also what was actually done for the COVID-19 vaccine of Janssen. Now, when we freeze a small solution containing water and whatever kind of solids we are interested in vials, then stochastic nucleation actually plays a big role. And you see here on the left a sketch of the freezing process, and on the right you see a typical thermal evolution curve. So let me start with this curve first. In black, we see the temperature evolution of the solution in the vial as measured through a thermocouple. In blue, we see a set point temperature of our freezing device, which is in the case of Crystal16. And in pink, we see the equilibrium freezing point, which is for most aqueous solutions just a bit below 0 degrees. And the interesting thing is, if you look at where the scale starts, we are already below 0 degrees. We are below the equilibrium. We follow the blue line closely, but then at some point we have a sudden rise in temperature. We stay up to the equilibrium, and then we cool down again. And what happens here is the following, that we actually, for all this time here, we are still in liquid state. We are super cooled, meaning we are at a temperature where ice could form, but in order to do so, this phase transition from the liquid to the solid has to be initiated by the formation of a nucleus. And this nucleus is not very likely to form if we are just a bit below the equilibrium temperature, but it requires a pretty big temperature difference to happen eventually. And this is a problem, because during all this time here, we are actually in the liquid state. And this has a major impact on the process performance and also on the product properties. Because if you don't know when actually your ice formation starts, it's very hard to design the process. And if you have complex biomolecules, there's also the thing that depending on at which temperature nucleation actually happens, you will have different product properties like residual drug activities and so on. So you actually want to know precisely at which point in time nucleation happens. And it's difficult, because nucleation is a rare event followed by rapid growth. And this is important to understand. So we are in the liquid state. At some point, we form a random nucleus, and this is followed by very rapid crystal growth. And this crystal growth is actually the reason for this rapid rise in temperature to the equilibrium here. So we have a slow process, which is nucleation, which can happen at any time, which is followed by a fast process responsible for this increase in temperature. Now, what this practically means, and this is now very relevant, is that only a single primary nucleation event takes place. Because as soon as a nucleation event happens, a nucleus is formed, and then growth happens everywhere because it's so fast. But because growth happens everywhere, this first nucleus actually completely governs what happens in the vial, and we have only one nucleation event. And if we have a situation like this, that we have a rare event, which is an activated process, then we have a lot of stochasticity. So what this curve here shows, now in black, are actually measurements of nucleation temperatures for about 200 vials. And we have the fraction of nucleated vials versus the temperature at which nucleation happens. And of course, if we are at very low temperature, then eventually nucleation will have happened everywhere. But what we see is that there's actually spread of several degrees when nucleation happens. So in the earliest cases, nucleation happens here already close to minus 10 degrees, but in some cases it's below minus 15 degrees, so it's a spread of around 5 degrees. And that's the problem. And of course, the solution to this problem is also shown here. It's the line in pink. This is kind of the best fit that we can get with a stochastic nucleation model, which is of course something that we want to have, because if we integrate something like this into a process model for freezing, we can understand the impact that nucleation has. And this is the focus of today. So I would like to really explain two things. The first one is how we can actually measure ice nucleation kinetics to better understand this phenomenon on a quantitative scale. And this is something we do in the Crystal16. And the second thing is I would like to underline how this actually plays a role into the commercial freezing process. If we look at the pallet scale freezing for the Janssen COVID-19 vaccine, which is the process for which we analyzed also engineering run data, and we have a mechanistic model. Now you see a couple more points here on this slide, and I would like to highlight that we have actually quite a few research activities here. So in order to come up with this large-scale mechanistic freezing model for pallet freezing, we actually had to build up complexity in multiple steps. So first we looked into freezing within a single vial with spatial resolution. Then we were simulating freezing at process scale with a large but not very large number of vials that actually interact with each other. And then we went up to the pallet. Similarly, we also carry out our own experiments in multiple devices. So we have not only the Crystal16, but also laboratory scale freeze dryer, where we can do freeze drying experiments with a couple hundreds of vials. And we also use, in collaboration with other research groups at ETH, a microfluidic setup, which allows us to study freezing in small microdroplets with diameters on the order of 50 to 100 microns to do some studies on the volume dependency of nucleation, which is also quite important. And this is kind of an overview of what we are doing. Let me now start with the first point, measuring ice nucleation kinetics. So as the title of the webinar already implied, we use the Crystal16 for this. And I would like to start with a photo here that shows our setup. So what we are using is the Crystal16 of the second generation. There is actually by now a third generation, which looks a bit different. This is why I emphasize this here. And over the course of the last couple of years, we actually made together with Technobis a couple of upgrades to this device. Now, the first thing that you will notice is that we actually have these additional holders here that are connected to thermocouples with these green cables. And the idea is that we have a system where we can put a thermocouple into every vial, which gives us a more accurate temperature information. Now, the second thing is, if you look on the right side here, you will see a connection to a thermostat. And this is something that we had to integrate because we realized that for the standard configuration, the cooling performance was not sufficient to study freezing. Because what we really have to do is we have to go down to temperatures of minus 35 degrees, and we need enough cooling capacity to remove the latent heat of freezing. So for this, we need to connect the Crystal16 to a thermostat to have some additional external cooling. And I should also say, I mean, minus 35 degrees is now the temperature limit that we have. And this is significantly below the specifications of the device. And we actually did not have any hardware problem with this. So this is actually something that now with these modifications works very well. And the minor thing is we also had to remove the lower temperature limitation of the software because the software had a hard-coded limit of -25 degrees. But this is, of course, just a minor change. Let me quickly mention how we can actually detect nucleation out of this device. We have actually two ways of doing this. One is with the thermocouples, and the second one is with transmissivity sensors, because already in-house, every vial or every hole for a vial is actually equipped with a transmissivity sensor, which is basically a laser diode, where you can have a laser going through the vial if it's transparent and not going through it if it's not transparent. And the thing is, if you freeze something, basically you go from a transparent liquid to a non-transparent, partially frozen system. So it's very easy to detect nucleation with transmissivity. And of course, it's also easy to detect nucleation with thermocouples because, as discussed before, we have a very strong rise in temperature. Now, the question is, which one of the two methods should we use? And in principle, thermocouples provide more accurate temperature information. So we use them a lot, and this is also the focus of today's presentation. But I have to highlight that thermocouples come with one big disadvantage. And this is that they may actually promote heterogeneous nucleation, because in order to immerse them into the vial, we have to open the vial, which means dust particles can enter. And of course, we also have to add the thermocouple. And the thermocouple itself provides a surface which may promote nucleation. So on the other hand, transmissivity measurement is something that is non-invasive. And this is very useful if we have, for example, sterile samples where we don't want to contaminate the system with more impurities or the thermocouple surface. And if you think about it, the application of this is really biopharmaceuticals, then it's clear that this non-invasive transmissivity measurement is also quite important. So for this reason, we actually developed techniques to use both methods. And we have seen that actually in the case of samples prepared under standard conditions in the lab, there was not a big difference. So let me come to an example for how we actually now do experiments. A typical experimental protocol looks like this. So we start from ambient temperature and we go to a temperature as low as we need. In this case, just down to -20 degrees because we have relatively early nucleation. And we do this a couple of times in sequence to generate more data points. So we will have 15 or 16 vials in the device, and then we typically do 12 cycles to have an experiment finish in a bit less than 1 day. And with this, we get a data set of about 200 data points, which is a very nice size to do some proper statistical analysis. Now, for this statistical analysis, we need to identify an appropriate stochastic model for nucleation. And those of you who already have some experience with nucleation know these models already from the case of primary nucleation of solution. And the idea here is kind of similar. We describe nucleation as an inhomogeneous Poisson process, which gives us the fraction of nucleated vials, which has the dimension of cumulative probability, as a function of this property Kv, which is the nucleation frequency. And the idea here is that the nucleation frequency is a deterministic quantity that gives us the likelihood that nucleation happens at a certain point in time. And we call this an inhomogeneous process because this can change over time, because obviously we are cooling down and the likelihood of nucleation has to be a function of temperature. So typically this nucleation frequency is expressed as the product of a nucleation rate and volume. But I have to say that there is one conceptual difference here compared to the typical experiments that you do in crystallization from solution. And this is that we actually do not steer our vials. So we might actually run into the situation that we have temperature gradients happening. And in this case, we have to integrate the nucleation rate throughout the volume. And we can actually end up with different outcomes for the nucleation frequency if we have strong temperature gradients. Now, for the nucleation rate, we can have different approaches. We could use an approach based on classical nucleation theory, for example. But what we do here is actually something simpler. we do power law of the supercooling, which is the temperature difference between the equilibrium temperature and the actual temperature of the vial. And this is actually something that we also have studied separately, that this is actually a good way of doing it. Another difference to isothermal experiments here is that we estimate directly the parameters in the rate expression, which are in this case the Kb and B, not the rate J. Because this is something that you would typically do in crystallization room solution. You cool down very fast to a certain temperature, you hold there, and then you can just measure the times at which nucleation happened, which gives you a value of the J. But what we do have a polythermal experiment with a constant cooling rate, which works a bit differently. And of course, you see here the best quality fit that we have for the optimized parameters Kb and B, and it looks very nice, right? So in a way, we can be happy that we have this close agreement between model and experiments. But of course, as everyone knows, just because you have a good agreement in one quantity between simulations and experiments, this does not mean that your model is necessarily good, independent of how you now want to define actually what is good and what is not good, right? So there are a couple of additional things we actually had to look into, and this is kind of what I spent a large part of my PhD in. I will only discuss the first one here, and this is if this description of nucleation as a Poisson process, as we do here, is actually accurate. We also looked into if this kinetic rate expression, so this equation for J, is actually accurate, which it is very luckily. And we also looked into if temperature gradients are relevant. And for this, I will also shortly discuss a bit later the model that we have. So let's look into this question if the Poisson description of nucleation is accurate. And for this, I have here now a set of experimental data and two different sets of simulations. Let's now firstly just look at the black experimental curve. What this here is really the raw nucleation temperatures for 60 vials. So we did 4 experiments with 15 vials each, and we arranged these vials in the order of mean nucleation temperature. And what we see here is that some vials actually nucleate very high. For example, the highest one always nucleates above -12 degrees, and some vials nucleate very low. A couple of them always nucleate below -15 degrees. And the question is, why is this the case? Now, the first thing we have to consider is, do we maybe have some errors here in how we measure thermocouples? Because, of course, every vial is immersed with a different thermocouple. So we had to do a study on the batch of thermocouples, what is our precision there? And we found that actually the thermocouples do not deviate by more than 0.3 Kelvin between each other, which is actually an order of magnitude less than the variability that we see here. So this is very much not an effect of the precision of our temperature readout. Rather, it's an effect of nucleation itself, because isonucleation is widely known to occur heterogeneously, meaning it is happening on surfaces provided by impurities. But this means in practice that some vials might actually have different impurities from other vials, which leads to this variability. And this is an effect that is actually now described for the first time for vials, but there is already some literature on freezing in microdroplets, so we can actually be confident that this is something that is kind of general. So how do we deal with this? In a way, we have to extend the stochastic description of nucleation, but we will not replace the Poisson process, but we will add something to it, because we know that in each vial, where we now have a specific set of heterogeneous nucleation sites, we are still stochastic. And we also see that the spread of nucleation temperatures in the individual vials is more or less similar for all of them. So we will keep the Poisson, but we will add something. And what we add is a vial dependency to the prefactor Kb. The idea is that we say that this Kb factor, it scales with the number of nucleation sites. So in some vials, you might have more sites than in others. And those vials that have more nucleation sites will simply nucleate higher. And because we have no control over this distribution of the prefactor, we use the very generic log norm distribution to simulate it, where we have a constant parameter and basically a standard deviation, where we have a distribution between the vials. So we can describe now Kb with two parameters, A and C. And we also have the exponential parameter b, so we have in total 3 parameters. And the question is if this is now actually better. And for this, I have 2 figures. The one on the left that shows sets of simulations generated through Monte Carlo simulations that gives kind of a way to visually appreciate the difference, and then also a quantitative study. If you look at the left, we have in blue the simulations with the new extended model, and in red the simulations with the old basic model. And if you just look at how this looks like, you know, the behavior of these vials, you see that you have actually much closer agreement between blue and black compared to the basic vial independent model. And the reason is that if the vial independent model, we actually do not manage to distinguish between a difference between vials and a difference within vials. So we have very broad distributions for every vial, but basically all the vials are the same, which is not the case if we introduce this vial dependency. We can quantify this by looking at different statistical quantities here. So the first one is the total variability. This is the one that we have already seen on the slide before. And we see that both models actually fit very well the experimental behavior. So this shows us that this fraction of nucleated vials versus nucleation temperature is actually not sufficient to really get such a model, to really optimize these parameters. And what we have to look at as well is what we call the external and the internal variability, which is basically how much spread in nucleation temperatures do we have between vials here and among between vials and within vials here. And in both cases, the vial dependent model in blue actually provides a much closer description. So we can really say that we have a superior agreement with this extended model. And of course, we did also more studies than I show here. So we also did some studies on the predictive capabilities, where we showed that this model describes cooling rate dependency more closely. So we are really certain that this is something that actually helps to improve the predictions. Now, with that being said, now that we are confident of the model that we have to describe stochastic nucleation, we can look into this in the commercial freezing process. I mean, so far we had a single vial freezing, but now we want to look into really the commercial scale freezing process. And for this, I would like to introduce something which is SNOW, in short of stochastic nucleation of water, which is the mechanistic freezing model that we have developed, which we provide also open access to it in form of a Python package. Now, this model is based on first principles, where we consider the stochastic nature of ice nucleation in the way that I just explained before. But of course, now we have to combine this also to a heat transfer model to describe the thermal evolution in these vials. It's applicable to an arbitrary number of vials. On the one hand, really large-scale things to a shelf or pallet of vials, or to a single vial with spatial resolution. And again, it's actually available open source as a Python package. Now, what do we get from this model? So if we do a single vial simulation now without spatial resolution, so kind of the most simple thing you can do, you will get the evolution of temperature in this vial. And you can also, if you run this simulation multiple times, get a stochasticity of it. So you see here kind of a spread in the time and the temperature when nucleation happens. And of course, if we just have a single vial, this is not yet very interesting. If we have a large number of vials, it's not very efficient anymore to get all these temperature evolution curves. So we can also just get the time and temperature when nucleation happens, and the time that we need to solidify completely, so to transform most of the water into ice. And if we have a batch, we can also measure the process duration, which is just the time when the last vial in the batch is completely solidified. Now, these quantities are interesting because depending on what drug product you have, your stability analysis may actually reveal that you want to have a specific range of nucleation temperatures or solidification times, or you might also have a limit for how long the entire process should take. So you can actually really, based on the needs for your drug product, design the freezing process. Now, I would like to show one slide quickly on freezing in a single vial, and then we will go to the pallet, because I have to make one point clear here, and this is about the temperature gradients within the vials, which I already mentioned in the very beginning. So what you see here is the simulation for temperature evolution with spatial resolution now in a very simple case. So we have a cylindrical vial where we have spatial discretization in vertical direction, and the heat transfer is just dominated by the shelf, so basically by the surface the vial stands on, which is temperature controlled as shown by the dotted line here. And of course, if we cool down the shelf, we will cool down also the solution in the vial. But the bottom here shown in black actually cools down more and faster than the top shown in green. So we have temperature gradients both before and after the time of nucleation. And the question is, do these temperature gradients matter? And what we can do with this model is we can actually calculate the likelihood that nucleation happens at different positions. So this is now a figure that shows you for 10,000 simulations of this process where nucleation happened. So we have nucleation position, 0 is bottom, 10 millimeter is top, and probability of nucleation on the vertical axis. And we have done this for 2 cooling rates. In red, we have a slow cooling rate, 0.1 Kelvin per minute. And you see that these bars here are more or less similar in terms of height in all positions. So nucleation is more or less happening with the same likelihood everywhere in the vial, which indicates that gradients don't really have a strong effect. But if we have a faster cooling rate of 1 degree per minute, we see that most nucleation events actually happen in the first 20% of the vial counted from the bottom, so in the first 2 millimeters from the bottom. So this means that the rate of nucleation really depends a lot on position when we have sufficiently fast cooling. Which actually tells us one thing, and this is if we have a very fast process, then we have to consider the effect of temperature gradients. But if we have a slow process, and it is very much the case for something like pallet freezing, which happens over the course of days, then we can neglect it. And that's important, because if we have such a pallet with tens of thousands of vials, then of course you cannot really simulate this with spatial resolution because of the high computational cost. But now we can do this without doing so, where we just say we have a single temperature value for each vial, which helps a lot. So let's now look at such a pallet. And this is now our model system here shown. This is the setup that was used actually to freeze the COVID vaccine with about 26,000 vials densely packed together in this pallet. And here I show some experimental data actually from engineering runs, where a small number of thermocouples was inserted into vials distributed in this pallet. There are 2 runs now, one engineering run at -20 degrees and one engineering run at -40 degrees. And there are a couple of phenomena I would like to highlight. The first thing is that we see these thermal spikes. And of course, we see big ones that we already know from the simulations I shown before that this is actually related to nucleation. But we also see a large number of smaller spikes, and we see them in both runs actually. We also see a stationary phase for some vials in the -40 degrees run. So the green vials actually are those that are close to the core of the pellet. And we see that over the course of many hours, the temperature here is essentially constant. And that's interesting, and we have to understand why this is the case. We also see that the process actually takes much longer in -20 degrees compared to -40 degrees. So it needs less than 2 days at -40, but it needed around 200 hours at -20. And in a way, it makes sense that this process needs more time if we are at higher temperature, but it's not clear how much more time it should actually need. So is a 5-fold increase maybe more than what we would expect? And we also see some variability in thermal evolution among the vials. So we see here for the -40 degree one that the inner vials actually have very different thermal evolution profile from the outer vials, while it is not the case for -20. And the idea now is that we use our freezing model to really simulate this process to better understand what's going on here. So we have simulated a system with 26,000 vials, now not with the COVID vaccine, but with 1 milliliter sucrose solution. But for this, we really actually measured the kinetics so we can be confident in what we are doing. And I show here a single thermal evolution curve. And this is for one vial in the core of the pallet, just because I want to highlight the key features. And in one case, in pink, we have done it with stochastic nucleation. And in one case, I've done it in black with instantaneous nucleation, where isolation starts already as soon as we reach the supercooled state. And the reason why I show this comparison between black and pink is because this instantaneous case is kind of the state of the art in freezing modeling. So, of course, we are not the first ones to simulate freezing, but we are the first ones to simulate it with stochastic nucleation. So when we started to collaborate with our industrial collaborators, the black line was actually what was used already in the company. In fact, not even the black line, but something was a bit simpler than this. But this is really, I think, very clear that with this black thing, you cannot really capture what the process is actually looking like. Although, of course, you already get some information with it, right? But the key point really is that with this stochastic model, we can reproduce these experimental trends that we have seen before. And I would like to highlight a couple of things here. The first one is we see thermal spikes, right? We see one big spike as seen before that shows us when nucleation happens actually in the vial that we monitor with the thermocouple. But we can also see nucleation events in the neighbors. So in this case, we have a configuration where each vial has 6 neighbors. So basically 2 in each dimension, so left, right, top, bottom, and also front, back. And what we can see is that we have actually 6 spikes that are a bit higher than the others, right? So we have here 1, 2, 3, 4, and here 5 and 6. So these are the 6 nucleation events in neighboring vials. And this really shows us that nucleation has an effect that goes beyond the individual vial. But as soon as we nucleate, we release latent heat, which affects the neighborhood. And this has a big impact on the entire process performance, leading to all these spikes. Now, we also see that we have this stationary phase where over the course of a very long period of time, the temperature is more or less constant. And this is actually something that is governed by nucleation kinetics. So the lower nucleation is, the lower the temperature of this phase is. And of course, now that we compare a case of instantaneous nucleation with slow stochastic nucleation, we see that nucleation has a very big impact on the process duration because the heat transfer parameters for this simulation and for these simulations are the same. So the increase in duration here is just due to the fact that nucleation happens at low temperatures. And this shows us really that stochastic ice nucleation has a governing effect on the process, right? It really governs the time that is needed to complete the process, but also the thermal evolution during the process. So really, if you don't consider stochastic nucleation, you basically cannot get a meaningful model of pallet freezing. And with that being said, I'm at the end of my presentations. To summarize the 2 points, right? First, we really developed and extensively validated a method to measure the ice nucleation kinetics in vials. And then secondly, we developed these mechanistic freezing models that allow us to study freezing at multiple scales from the freezing of a single vial really up towards the pallet scale. And we open sourced this model, so every one of you can just download it. And I can really recommend to look into it if you work into freezing. And here on the bottom, you see the relevant publications associated to it. All of it is open access, so you can have a look at it as well. I would like to acknowledge, of course, the support from the pharmaceutical companies of Johnson & Johnson, especially the 2 senior scientists, Juan Arak and Ryan Wall. And if you want to reach out to me, please feel free to contact me under the information here, or also my colleague Andras Koshia, who is now working with me full-time on the topic. Now, thanks a lot to all of you for listening, and I really hope that you appreciated this webinar. Thank you.
Thank you very much, Leif. Really interesting, and for me, it's the second time I hear you talking. We met last year, actually, is when I saw for the first time the presentation. Really interesting topic and great work that you have done here. I had a few questions also myself. Besides that, I wanted to mention that actually the Crystal16 version 3, how we call it, or the latest version, actually now you can connect it to, also to a chiller. It can go to these low temperatures as well. You don't have to modify it. It's already adapted if needed to go to these low temperatures. And actually, this setup that you have here with the thermocouples and to be able to measure the temperature inside of the vial, it is also a separate module that now we provide to our customers for these more specific type of applications. It looks a bit different, not really like a development project like this one, but in principle doing exactly the same. I think we call it the measurement device, temperature measurement device. Besides that, indeed, actually, these modifications that we have done for you guys for ETH, some of these modifications inspired us also in the next generation, the version 3 Crystal16. So we are deeply thankful to you and to our customers. We always develop from the needs of our customers. Sometimes now going back to a bit more science, I do recall because you were showing, I think on slide number 9, or this your protocol, yes, experimental protocol, and I see there you have actually 20 cycles. I do recall a paper since quite a few years back. I think it was still from Marco Mazzotti's group, where they were looking into this number of cycles that you actually need to perform to get good statistics out of it. But I do not recall if I'm missing some information or I do not recall right, but I think they were about 80 cycles, a minimum of 80 cycles related to that. I see you have just above 20. How much did you use here, and what can you say about that?
I think that's a good question, right? Because in a way, with these stochastic nucleation things,
yeah,
independent of freezing now or for crystallization, the question is always how much data points do you need, right?
Yeah.
Because this distribution will, of course, look more beautiful, more like a real distribution if you have more data points, right?
Yeah.
And the key point in crystallization is kind of the number of data points, which is then the product of the number of vials, which is mostly 16, times the number of cycles.
Yeah.
So the value of 80 you refer to is the product of 16 vials and let's say 5 cycles. So you can, in principle, do such an experiment in one day, right?
Yeah, indeed.
Now, one more comment about this, and this is the problem that you have with crystallization is that you have to do these experiments under isothermal conditions. So it's not like we cool down here with a constant cooling rate and can be sure that one cycle is finished in an hour or so, because we know if we get cold enough, nucleation will happen, right?
Yeah.
But you have to crash cool to a certain temperature in crystallization, and you hold there. And it can be that you have to hold there for hours until nucleation happened everywhere. So typically, a single experiment for crystallization takes maybe 2 or 3 times more time than what I showed here. So we can actually, get more data with this approach.
Yeah. And because you were talking about also the cooling rate, what is the cooling rate that you have used? Of course, again, versus crystallization, as you said, when you heat up and then you cool, it's different. But what did you use here?
So we tested actually a couple of different cooling rates, and the reason for this was the issue with the temperature gradient. So
yes,
in the end, the cooling rate that we mostly use is 0.6 Kelvin per minute, because we've realized there that gradients don't yet have a big effect, but we already have a good throughput. Because if we go, for example, to 0.2 Kelvin per minute, which we also did, then of course we need much more time for each cycle and our throughput is smaller. So in a way, there is an optimum somewhere, right? Very fast cooling rates don't work because you have the temperature gradients, and very slow cooling rates mean that your experiment takes forever. So really, somewhere at half
in between. Yeah. And I think this is also, well, also not only for this specific case study, but also for crystallization, the same. What I do recall is that indeed for the temperature control in version 2, in the Crystal16 version 2, or let's put it differently, in the temperature control in the latest generation that we have now, it is improved. And we have performed quite a few studies also looking at the cooling rate for induction time measurements, for example. We noticed that actually we investigated several cooling rates. We looked at even 20 super fast, just you do it really fast, or 5 degrees, or even lower. And actually the accuracy is much higher, depending on how accurate you want the data and how problematic or less problematic, let's say, is the system, the compound that you are working with. In some cases, even 20 degrees per minute was quite good enough for just having an impression idea. In a bit more slightly complicated cases, the 5 degrees was ideal to cool down this rate. And of course, we also did a combination with the feedback control software. I don't know if you have the feedback control software on your instrument.
Not sure, actually. Yeah.
And the way that you trigger actually the change from one cycle to another one is not by temperature, but by transmissivity. So once it's detected that you have something crystallizing out, forming in your solution, then you it automatically goes to the next step. So the few degrees you save some time, of course, if you have to do a lot of
cool feature. No, I'm pretty sure we don't have it actually the way you describe it. I think especially for crystallization, if this you can save a lot of time. Yeah.
Yes, indeed. For crystallization, indeed, there is really an added value. Okay, I think this is it. Thank you very much once again, Live. We are going to share this recording in an email with our with who registered and the attendees, and you will also receive an email. If we receive any questions, I will also share them with you to address them, or I think if anybody has a question, can also write to you directly, right?
Please feel free to just let me know and write me directly via email. Yeah.
Yes, super. Perfect. Once again, thank you very much, and hope to see you soon, Leif.
Thanks a lot for giving me the opportunity to present here. Thanks, Carmen.
Thank you. Bye.
Bye-bye.